Welcome to week 2. We're going to cover position vectors and moments and some cross products. This is chapter 3, problem 34 from the book. So first of all, let's start off with some definitions and equations. A unit vector, it specifies the direction of a given vector and it has a magnitude of 1. We determine the unit vector by taking a vector and dividing it by its magnitude, which you'll need to know. A position vector is a fixed vector r which locates a point in space relative to another point, so it could either be from the origin to a certain point or from one point to another. Finally, in order to find a force vector from a scalar force, you should know that you have to take the scalar and multiply it by the unit vector, because the scalar gives you the magnitude and the unit vector gives you the direction, and that's basically what a force vector is, a force with a direction. Also, you need to know how to do cross product. I hope you guys remember A cross B. You create this matrix, and if you don't, you should probably get a little refresher on that, because in order to find the moment from a certain force, you need to do R cross F. And something to help you visualize, let's say we have point O and we have this position vector R and this force going in this direction. If we do R cross F, then the moment will point upwards, because I like to use the right hand rule. Let's say R, you point your pointer finger that way based on the position vector, and B, you point your middle finger towards the force, and wherever your thumb points, that is the direction in the resultant moment. So I hope you understand that and get used to the right hand rule. It's very helpful. Also, the way that your fingers curl, so in this case they're curling this way, that basically means that that's the rotation that will occur based on the forces and the way that they're causing the moment. So a rotation will occur this way. So here's the problem. We have a flagpole and two ropes, so two forces, Fc and Fb. Determine the resultant moment produced by forces Fb and Fc about point O. Point O is down here, it's the origin, what I'll call it, and we must express the resultant moment as a Cartesian vector. So right now, let's point out the fact that we have the forces as scalars. We do not have them as vectors. That means we need to convert them into vectors. So here I like to think of a process where we take everything one step at a time. The first thing, we need to determine position vectors. From the position vectors, we need to determine the unit vector. And from that unit vector, we can use the scalar force to find a force vector. And we use the force vectors and the position vectors to determine a resultant moment. This will make more sense as we start doing the process. So here's another image. I'm going to use this one from now on just because it's more clear. So first of all, I want to start off with FC. I want to find the position vector of FC. So FC is pointing from A to C. That means we need to find the position vector from the origin to A, from the origin to C, in order to find this position vector from A to C. So RA, or the position vector to A, is 0, 0, and 6 up. RC is 2 in the x direction, 3 in the negative y direction, and 0 in the z direction. So I, j, and k just mean x, y, and z. So in order to find AC, all we have to do is take RC minus RA. And that gives us 2i minus 3j minus 6k. So now we have determined the position vector from A to C. From there, we want to find the unit vector, AC. So the unit vector is defined as the position vector divided by its magnitude. So we already determined the position vector previously, and in order to find the magnitude, we just take the square root of x squared plus y squared plus z squared, and that gives us 7. So now we know our vector, we know our magnitude, we determine the unit vector by taking the vector divided by the magnitude, and this is our unit vector. The unit vector specifies the direction, the direction of AC, so we can use it to find the force vector. So here's our unit vector. Our force vector we find by taking the scalar, which is 420, and multiplying by the unit vector, which we just found. So it's pretty simple, 420 times all of this, and you end up with your force vector for FC. Always remember your units, that's important. Now that we found our force vector for FC, we move on and do the exact same thing for FB. So we want to find the position vector from A to B. So we start with the origin to A, the origin to B, and that will eventually give us AB. So RA is 6 up, RB is 2.5 in the Y direction. And now we want to find AB. So we just do RB minus RA, and that gives us RAB. So 2.5J minus 6K. From there we find the unit vector, the vector divided by the magnitude. So our vector we just determined, the magnitude once again is x squared plus y squared plus z squared, square root. So our unit vector for AB is this final answer. So now that we found the unit vector for AB, we can find the force vector. So the same thing as FC. The force vector is equal to the magnitude of the force, 780, times the unit vector that we just found. So 780 times all of this gives me 300J minus 720K newtons. Okay, so now we have determined both of our forces, FC and FB, in vectors. So what we need to do, they asked us to find the moment produced by FB and FC about point O. So the moment is defined as R cross F. So we need to do cross products here. So I want the vector, the position vector from O to A, because that is the direct vector that connects both to FC and FB. And then I have FC and FB, right? So I'm going to individually cross this position vector with FB and this position vector with FC, and that'll give us the two moments caused by the two different forces. But because we have two forces, we can just add them together and do RA cross FB plus FC. So here I'm just adding the two force vectors, and this is just the original position vector from O to A. It's just 6 up, right? 6K. So I end up with my original position vector, which is 0I, 0J plus 6K, and a new force vector, which is just the summation of FB and FC. And I end up with 120I, 120J minus 1080K. So from here, I just want to take the cross product of these two. But we need to keep in mind that it's always R cross F, so R always needs to remain first and then the force. So the cross product, you create your little matrix, IJK. This is all of the coefficients of R and all of the coefficients of the force. So remind yourself how to do cross product. It's fairly easy. You for all the I, you look at this section. For all J, you eliminate this middle section. For all of K, you look at all of these. So remind yourself how to do these, and in the end, once you do all the multiplication and addition, you end up with the moment about point O being negative 720I plus 720J newtons times meters. So always remember, it's important to remember your direction. Is it negative, positive, is it I, J, or K? And do not forget your units, because points will be taken off, most definitely. So the most important thing here is to take everything one step at a time. If you understand what a position vector is and a unit vector, you can easily find the force vector, right? As long as you understand the basic definitions of all of these terms, then you should easily be able to find the resultant moment, knowing that it is R cross F. So you just need to find out what your R is, find out what your force vectors are. Is there only one force vector? Are there many force vectors? Can I sum them? Etc. So pay attention to the detail, and this is a fairly complex problem, I would say. I mean, as long as you know the basics, it's just going through a certain process. I hope that helps you guys, and see you next week.